All right, how's it going? Welcome back to another video here in the series on linear algebra. You might have noticed that we have changed the section title, right? I think the last one was looking at vectors, and now it says this thing called linear maps. So whenever we move on to a new section, it's always good to put in context what we have been doing so far, right? So really up until this point, we have been talking all about this thing, this algebraic object called the vector space. So we can write vector space. And specifically, the way that we have been studying a vector space has been to look at the components or the elements of a vector space, which were called vectors, right? So maybe if this were to represent a set corresponding to a vector space, maybe these individual dots are vectors inside the vector space, right? I mean, we've spent a lot of time now talking about what these vectors are, both in terms of their definition, things that can interact with other vectors through vector addition, and things that can also interact with scalars, which we can think of just as real numbers through scalar multiplication. And that's what they are by definition. And then we've also talked about vectors intuitively, right? Kind of like these arrows that point out in space. So this has essentially been the picture, I guess, the grand picture overall. We've been saying, let's look at this bubble and let's look at the little dots inside the bubble. Now, though, that we are in a new section here, we want to take a slightly more, I guess, dynamic approach to everything that's going on here. Because so far we've been talking about how vectors can, or elements, or like the dots inside this bubble, can interact with each other, kind of like movement within the bubble. But what if, for example, we don't just have one vector space, and maybe rather than just writing the word vector space, I'll just give this a compact letter, A. But what if we also have another vector space, B, and maybe it has its own vectors contained in it? And what if, rather than just looking at one of these vector spaces in isolation, we want to move or sort of map from one vector space into another? And it turns out that there are ways to do that, right? And hopefully we're familiar with the idea of a function, which we could call f, right? Where we could say that f maps from a domain A into a codomain B. An arbitrary function is simply going to be a function that maps from any one set into another set. And really the only property of a function that must be satisfied is that every element in the domain set needs to map to a single corresponding element in the codomain set. Okay? And really that's the only, I guess, restriction on just a general function, or a general map, I should say. But you might be able to tell, though, also that by the name of the section title, we are not just going to be interested in any type of map. We are going to be interested in maps that have a specific property known as linear maps. After all, hope that makes sense, right? If we are studying linear algebra, we inherently want to study the algebra of linear maps. Okay. So we're going to be interested in these types of functions now in this section, but these types of functions are going to have a very specific property. So the goal for this video then is to introduce what these objects are, or I guess what these maps are between vector spaces. What is a linear map? What are some of its basic properties according to their definition? And then we also want to develop an intuition for a linear map. When we think of a linear map, what should we be visualizing in our head? And I want to do that, of course, so that way we can kind of go along the same lines of what we've been doing so far. Like with vectors, we introduce both a definition and an intuition. We want to just keep that same sort of double-sided road, or whatever you call it, where we have both the mathematical structure but also the visual picture to help us understand these concepts. Okay. So hopefully that makes sense. what I'm going to do first is, well, I guess, erase just this, and first write out what the definition of a linear map is. What is a linear function going from one domain into a codomain? Okay, so I'm going to do that now, and then we're going to go through that together. Okay, so have the definition for a linear map right here. Let's go through it together. So first thing is that we want to define two different vector spaces, and these are going to act as our domain and codomain sets. So let V and W be vector spaces, and we're going to define a map T, which maps the vector space V into the vector space W. Then we would say that T is a linear map if these two properties are satisfied. And we can, I guess, read them out, that if T of A plus B equals T of A plus T of B, and then T of lambda A equals lambda times T of A. And so these are the two, I guess, properties required for a linear map, but I want to make sure we understand why we want these specific properties and why we're interested in these specific properties. Okay, so to do this, I want to go back to just kind of the picture of looking at an overall vector space. Maybe I'll do this right here. So it says that we have a domain vector space, V, and a codomain vector space, W. Right, and we're saying that the map that we're going to be interested in, we're calling it T. Now, if we were to just look at, for a moment, just elements of this domain vector space V, maybe we can just put some dots in here just to represent elements of this vector space. First thing we ask is, well, what is an element of a vector space? Well, that is a vector, right? So these elements are going to map, these elements are inherently vectors, which is why in both of these properties right here, notice that the inputs into this function have the little hat over them, because the inputs to the function are going to be vectors, elements of a vector space. And if the elements of V are vectors, they need to map to elements of W. And elements of W, because W is a vector space, are also vectors. Which is why, if we look at the right-hand side of these two properties right here, that, well, I guess it's not immediately obvious, but hopefully it makes sense that if a vector needs to map to another vector, that T acting on, or T of A, this overall quantity needs to be a vector, and this overall quantity right here also needs to be a vector. Same with this quantity right here. So that's kind of the first thing that we just want to keep in mind, is that this function is mapping inherently vectors into other vectors. But the question still remains, why are these two properties important? Why do we care about these two properties? Well, let's go back to just the vector space, V, and think, how do the vectors in this vector space V interact with each other? And we know that there are two ways that elements of a vector space can interact, right? If we have two vectors inside V, maybe we'll call this dot right here A, and this dot right here B. These two vectors can interact with each other through vector addition, right? That was one of the properties of vectors. And maybe when these two vectors add, maybe they add up to some third vector, C. Maybe I'll call C that vector right there. I don't want to put too many letters because I didn't draw the bubbles big enough, right? But maybe A and B add up to get this third vector right here, C. What we care about then with this linear map T is that if we were to apply T to this equation, and this equation we got simply from saying, how do vectors interact? They interact just by how they're defined, through vector addition. If we were to apply T to this equation right here, we would hope that if we are going from one vector space into another vector space, that the same overall structure of vector addition still holds. So, and here's what I mean. If A plus B equals C, then we would hope that we are going to specifically care about functions that satisfy that T of A plus T of B equals T of C, like this. Okay. So hopefully this makes sense, right? Both before and after we apply the linear map, we see that the overall property of saying if you have two vectors, you can add them up to get the same third vector. This overall inherent structure that was defined in the vector space still holds. Now, to see how this relates, let's remind ourselves, what did C equal in the first place? Well, under this top line, C equaled A plus B. So if we replace C with A plus B, this is what we get. We get the same left-hand side of T of A plus T of B equals T. Now instead of C, I'm just going to write A plus B. And notice that is the first property for a linear map. Okay? So we're seeing that linear maps are the maps that preserve the structure defined in a vector space. And this first requirement was really for that first operation, vector addition. Now what was the second operation? What was the second way that vectors could, interact? And they could interact with scalars, which we're going to call lambda here, through scalar multiplication. And to see this second property right here, maybe I'll write something down here. We know that in the general case when we're looking at the map T, that if we have an element A in the domain, it will map to whatever T of A is in the codomain. Maybe this A maps to T of A in the codomain. Hopefully that's not too small, that we can still see that. All right. So because these are both vectors right here, they can both, this left-hand side and the right-hand side, can both interact with a scalar, like a real number, through scalar multiplication. So what I can do is I can multiply both by lambda, because that's how you interact a scalar with a vector, right? So I can take lambda times A, and that should map to, ideally, lambda times whatever this vector is, times T of A, okay? So hopefully we're seeing how this develops, right? If this is the input into the function, and let me be a little bit more specific, if we take T, our linear map, and have lambda A as the input into T, what we just stated should equal lambda times T of A, like this. And notice that is what this second property here states. So hopefully we're getting the big picture here. These by themselves are the definitions for what it means to be a linear map. But what a linear map is really doing is it's saying that as we're going from one vector space into another vector space, we're preserving the overall structure, the requirements for how vectors interact, going from one vector space into another. And that idea of preserving structure, of saying that if we have the properties of this vector space, we're going to have those same properties in the codomain vector space. That is why we're interested in linear maps in the first place. You can imagine if maybe you had some structure of vector addition and scalar multiplication in this domain vector space, and maybe that completely collapsed in the codomain vectors, in this codomain set, I should say. I mean, you could define a map that does that doesn't satisfy these properties, but then why are we interested in them in the first place, right? After all, if we are interested in vector spaces, we want to make sure the functions that we're working with satisfy the properties that they uphold the structure of a vector space. So hopefully that makes sense. Okay. I think one more thing that I want to do, because it can be a little bit feeling like checking off things on a checklist if you have requirement 1, requirement 2. These requirements can get combined together, and this is the way that most people, I would say, including myself, typically remember what it means to be a linear map. And the general idea is that rather than just having vector addition by itself and scalar multiplication by itself, you just combine both of those operations together. What is the most general way you can both multiply, or what is the most general way, I should say, you can have vector addition and scalar multiplication with 2 inputs? And the most general way you could write something is a linear combination of those 2 operations. So not only do you have A and B, they're added together, but they're also multiplied by their own respective scalars. So maybe I'll say lambda for the scalar multiplying A, and mu, just some other Greek letter, for the scalar multiplying B. And the general property, the way that most people remember what it means to be a linear map, is that if you have T, your linear map acting on this linear combination of input vectors. Well, actually, maybe if you're unsure, take a minute to pause and try to see how you could apply both of these together to get what the output should be. Okay, assuming we paused, right? Then the way that this would work is that first we see that T distributes across the sum and the scalars come out in both cases. So this would equal, let me erase this real quick. I want to make sure I have space for this. This should equal lambda times T of A plus mu times T of B. And this definition right here, the one that I just boxed, is really, I'd say, what people think of when they think of what does it mean for a linear map. T is a linear map if it satisfies this property right here. Okay, so hopefully that makes sense. Now, all of what we have been doing so far has been very sort of symbolic, very algebraic, and very much in thinking of the definition and in kind of that dual definition and intuition picture, right? Kind of like how when we started to talk about vectors, we said, okay, what is the definition of a vector? It's a thing that can add to other vectors and multiply by scalars, right? So what is the definition of a linear map? A function that preserves that structure that has this property. All of that is definition based. But what about now our intuition? How should we visualize these linear maps? How should we think of them, regardless of the fact that these are the actual definitions? Well, let's first remember what the intuition for a vector was. And maybe I'll start to erase, well, I can erase most of the stuff right here. And I'll keep talking as I'm erasing. But for our intuition for what a vector was, is that it was simply an arrow in space, right? And actually, let me just write out this definition one more time. So we have T of lambda A plus mu B equals lambda T of A plus mu T of B. Okay, so we have the definition, right? Now let's think of our intuition again for the how we should think of a vector. If we're working in R2, we can think of a vector visually as some arrow in 2-dimensional space. Maybe like this arrow right here. Maybe we could call this A. If we have another vector B, maybe that's this arrow down here, B. And we have come up with different ways to represent these vectors using different notations. Maybe these could be represented as columns, like column vectors, right? And the idea is that visually, if we can think of an individual vector as an arrow in space, so if here's a 2-dimensional space, you can imagine an arrow in 3-dimensional space for R3, and you can conceptualize an arrow in n-dimensional space for larger values of n. Then what I'd like to get across is that if we were to try to imagine not just one vector, not just 2 vectors, but what would the space of all possible vectors in R2 look like? Well, there would just be an arrow for each point in space, right? Maybe if this is maybe 2, 1, there would also be an arrow maybe that looks like 1, 2, that's like this. So this would be 1, 2. And then the 1, 1 arrow might be something like this. And you see how whatever the values are for your x and y coordinate, that would correspond to a different arrow. So R2 or R3 or Rn, whatever, every point in space has its own corresponding arrow. Visually, this is how we can imagine Rn, or for whatever value of n, right? Now this is getting a little bit messy. Let me stick with let's actually just stick with one vector for now, vector A. And let's suppose that this is the element of the domain that we are going to act T on, or that we're going to apply T to. Hopefully that makes sense. So this is A in the domain. Now that should map to T of A in the codomain, right? So let's try to draw out this codomain real quickly. And because this is going to take in one vector and map it to another vector, unless it's the identity map, which maps everything into itself, the codomain vector will not be the same as the domain vector, right? So the arrow that I draw in the codomains, so maybe let me even write this. This is the domain, and this is the codomain. The arrow that I draw in the codomain may not be the same, in the general case, will not be the same as the arrow in the domain. So maybe, rather than the arrow pointing like this, maybe I'll have the arrow point like this. So rather than having 2, 1, maybe the new coordinates, we'll say that T of A, let's see, T of A equals now maybe like 1, 3 or something. I don't know, just making something up, right? So visually what T is doing, this linear map, and this is really what I want to get at. What is the visualization for a linear map? What T is doing is it's taking an arrow and it's taking it, maybe it's first slanted like this, and then it slants up like this. So rather than thinking of it kind of as like two frozen pictures where like that's the before and that's the after, we can think of it kind of like a continuous sort of movie going from the before to the after. So hopefully this is going to make sense that if it starts like this, it ends like this. The way that it's going to do that is kind of to rotate up a little bit. It's going to start here and then it's going to rotate up to match whatever the final ending picture is. Okay? So when we think of a linear map, we can think of just moving. We can think of rotating or increasing the length or decreasing the length, or maybe decreasing the orientation or inverting the orientation of a vector. But we can think of it as a visual picture and not just the static before and after. But this vector is physically moving in space, and T is the mechanism that causes it to move in the first place. Hopefully that makes sense, because that's just a picture with one vector. I would take a minute to really let that sink in, especially if it's the first time hearing about this. And maybe I'll even say it again, that the way we can intuitively think of a linear map is a mechanism that causes a vector to transform, to move in some way, shape, or form. And we're going to see in later videos that actually it can't move in arbitrary ways. There are some restrictions. The restrictions are actually defined by this definition right here, but we'll see visually what those restrictions are. Regardless, we should think of a linear map as a mechanism that causes vectors to transform or to move in the vector space, to go from one arrow to another. Now, final thing before I erase the board and we go on to something new. And I know I'm spending a lot of time on this, but I think understanding both the definition and the intuition is really fundamental for the entire section. So I really want to take my time with this. a couple minutes ago, I was just drawing a bunch of different arrows in space, right? So we have this arrow, and we have this arrow, we had this arrow, we had arrows are going to be everywhere at every point in I guess if this is R2 in two-dimensional space. Well, we saw how the map affected one of those arrows, how it affected A going from here up to here, right? But what was going to be true for any map, regardless of if it was linear or not? Well, what's true of a general map is that every element in the domain, meaning every arrow in this space, needs to map to a single arrow, a single corresponding arrow in the codomain space. And that's important because what that tells us is that not only does A get rotated, but every vector, or I guess get rotated and then it probably increases its length a little bit because that's 3. But point is, not only does A transform from here up to here, but every vector in space is going to have that same transformation. That means this vector is going from here maybe down to here. This vector goes from here over to here, or something like that. So we can think of all the arrows in space as, I guess, rotating a little bit counterclockwise and maybe increasing their length by a little bit. So like there's this visualization, if you can imagine, a bunch of different arrows rotating and slightly enlarging. And that visual picture, that dynamic picture, T is doing that to every single arrow, every single vector in the domain vector space as it maps to the codomain vector space. Okay, so hopefully, I know this is a lot to take in, right? Especially if it's our first time hearing about it. But again, hopefully the visualization makes sense, and also the distinction between saying this is the definition of a linear map, and intuitively we can think of linear maps as these transformations of the arrows moving from one vector space into another. Okay. Now, when we have been probably when you have learned about functions for the first time, or just maps between sets for the first time, you first start talking about what is a function, how do you know where one element in the domain maps to one element in the codomain, and usually immediately after that, you start to talk about function subspaces, right? So whether you're talking about the things like the image or the kernel of a function, these are things that usually get introduced relatively soon after you talk about what a function is. So that's going to be the next natural progression here as well. Now that we have defined and talked visually about what a linear map is, let's start to talk about what the kernel and the image of a linear map are. Okay. So first I'm just going to write out the definition for what those are just to remind ourselves, and then we're going to unpack that and go through that together. Okay, so we have the definition for the image and the kernel of a map. And I should mention at the beginning of this that this is not anything specific for linear maps. This is true for any function or map that you're working with. So this hopefully shouldn't be anything new, but rather just kind of a reminder. So it's not like, oh, what's the image and what's the kernel again? Just so we have this in our head. So starting with the image, we're saying that if we have some function t, which goes from v to w, then the image of t is, I probably should even wrote that this should be the image of t. the image of t is going to be a subset of w, or in other words, a subset of the codomain. Okay, and that's kind of an important part, right? To say that it is going to specifically be the set of elements in the codomain which get mapped to from the domain, right? So this is the elements in the domain such that the input to this function t comes from the domain. And just maybe really quickly too, to see why this wouldn't just be all of the codomain in the first place, you could map from a smaller set into a larger set, right? And maybe you could have 1 maps to 1, 2 maps to 3, but nothing gets mapped to the number 2 in the codomain. So then we would say, and if this was an arbitrary function f, we would say that the image of f would just be the elements in the codomain that got mapped to from the domain, right? So it'd be the number 1 and the number 3. So that's what the image is. It's a subset of the codomain. And then for the kernel, which I probably should have written that this is the, let's do this, the kernel. Kernel is kind of, I shouldn't say the opposite, but it is a subset, not of the codomain, but it is a subset of the domain. Specifically, it is the elements in the domain V such that when the map gets applied to those elements, it maps to the corresponding 0 element in the codomain. Okay? So again, if we had, they get mapped to 0 in the codomain. So if we had the 0 element, which in our case would be the 0 vector, because we're talking about domains and codomains, which are vector spaces, and maybe we have elements A and B, which both map to the 0 vector. So we have T of A equals 0 and T of B equals 0. Then, and those are the only 2 elements in the domain V, which map to the 0 element in the codomain W, then we would say that the kernel of this map T would just be these 2 vectors, the vectors or the elements in the domain that map to 0 in the codomain, right? So it'd be A and B. And get out of the way there, right? Right. Again, hopefully this sounds familiar, and we've seen this at some point before. Now, assuming that this sounds familiar and that we're like, okay, yeah, that's what the image is, that's what the kernel is, what I want to do to finish off the video is I want to write out a theorem that is going to say, well, what are some specific things that we can state about the image in the kernel, not just of any map, but of a linear map? Okay, so we can kind of make some statements about some of the fundamental function subspaces for linear maps. All right, so given the 2 vector spaces V and W, and also given a linear map T, which maps from V into W, then here's what we can state. We can state that the image of T is a subspace of the codomain W, and the kernel of T is a subspace of V. Now, I want to make sure immediately that it is clear why this is significant, because before we were just saying that that given an arbitrary function, that the image is a subset of the codomain and the kernel is a subset of the domain. But we are not just saying a subset, we are saying a subspace, which is a slightly stronger statement. Now, I don't think, if I remember correctly, that we have covered vector subspaces yet. And the reason for that was simply because it feels like it's relatively intuitive, and we'll quickly go through it now, but what a vector subspace should be. If we're given a vector space V, then a vector subspace conceptually is just a subset of V, which maybe is U. And that subset also forms a vector space within itself. In other words, it satisfies the definitions and checks off all the axioms required for a vector space. Now, we might not remember, okay, well, what were all those axioms? And it turns out there's a relatively concise way to state that U is a vector subspace of V if this condition holds. So I'm going to write out what that condition is, but conceptually that's all a vector subspace is. It is a subset of a vector space that also forms its own vector space within itself. Okay, so relatively simple criteria. If we have a vector space V, then a subset U of this vector space V is considered a vector subspace if basically two criteria are satisfied. The first is that the subspace needs to be non-empty, so you can't have an empty vector space, can't be the empty set. And then also for all elements in the subspace, then we also need to have that all linear combinations, or I should say for any two elements in the subspace, then any linear combination of those two elements also needs to be in the subspace. Okay. So this is, again, just a compact way of essentially listing off the axioms of a vector space and just writing it out compactly. So the reason that I write that right here is because for proving this theorem, and maybe we'll write proof down here, is that when we want to show that the image and the kernel are vector subspaces of both V and W, I guess of W and V respectively, we just want to show that this criteria is satisfied. Okay, so hopefully that makes sense. We're going to be using this as a reference effectively. Now, one of the properties of linear maps is that if it is going to map one vector space it is going to be a map from one vector space into another, each vector space inherently will have what's like a zero element, the zero vector in that vector space. And one of the properties of linear maps that can be shown is that if you have the zero vector in the domain, and then you apply your linear map to that zero vector, then you will get the corresponding zero vector in the codomain. Okay? So it's going to map the zero vector, the domain zero, into the codomain zero vector. And that immediately is important, or just useful, because that immediately checks off the non-empty requirement. And let's see why. The image, again, that's the set of elements in the codomain that get mapped to from the domain. We know the zero vector is in the codomain because the zero vector from the domain gets mapped to that element. So the image would be non-empty. As for the kernel, the set of elements in the domain, which map to the zero in the codomain, we know that the zero in the domain, hopefully this is not too confusing, the zero in the domain maps to the zero or the identity element in the codomain. Therefore, the domain zero is a part of the kernel. So the kernel is non-empty. So simply from this property alone, sort of the identity maps to identity property, if we're talking in group theory, or in more just general algebraic terms, that immediately satisfies the requirement that both the image and the kernel are at least non-empty. So now what that means is that for the rest of the proof, all we really have to show is that for any two elements in the image or the kernel, then any linear combination of those two elements is also in the image or the kernel. And we're going to go through both. Let's start with, doesn't matter which one, but let's start with the image. So if we have two elements, any two elements in the image, and maybe we can call those, just to use the same notation, X and Y. Again, these are elements that are, elements in the image are inherently elements in the codomain, W. So if we have X and Y, and these are elements of the codomain W, what that tells us is that these elements got mapped to from some elements in the domain, right? So in other words, there needs to exist, so there exists A and B in the domain, such that when maybe T gets applied to A, that maps to X, like this. And then when T gets applied to B, maybe that maps to Y. Again, these requirements just come from the fact that x and y are in the image of t. Now, what we can do is we can say, okay, if this is the definition, we would like to also show that lambda of x plus mu of y is also in the image of t. Okay? So let's go through that. So if we now take lambda of x plus mu of y, some linear combination of those two vectors. And now what we do is we say, okay, let's just replace x and y with the left-hand sides of these equations. So x was the same thing as saying t acting on a. So rather than writing lambda of x, I'll just write lambda of t of a, like this. And then I have plus mu. And rather than writing the vector y, I can write t of b. So now I have this equation right here, lambda t of a plus mu times t of b. Now, because we are inherently working with a linear map, and not just an arbitrary map, we know something about linear maps. And that's like saying a linear combination of outputs is equal to a linear combination of inputs. That is, I guess, the compact, wordy way of just rewriting this equation. And this just came from the definition of a linear map that we had a couple whiteboards ago. This is the same thing by definition as t of lambda a plus mu b, like this. All right, going from here to here we just use the property of what it meant to be a linear map. And that's really important, right? Because we're saying that lambda x plus mu of y, that is an element of the codomain. And we just showed that it equaled t acting on lambda a plus mu of b in the domain. So there is some element in the domain that t acts on to get to this corresponding element in the codomain. Therefore, lambda x plus mu of y is in the image, so we can maybe even write it. Therefore, we could say lambda x plus mu of y is in the image of t, and therefore the image of t is a subspace of W, is a subspace of the codomain right here. Okay. Hopefully that is clear. Now this is just for the image, we still got to do this for the kernel. So let me maybe just erase this real quick and then we'll go through the kernel part of the proof. And it's pretty short and there's not a lot to erase, so I can even just probably talk while I'm erasing. But the kernel is just going to follow a similar structure. We've already shown that the kernel is non-empty. So now we just need to show that given two elements, x and y in the kernel, so we're going to say if we have x and y in the kernel of t, then we first say, okay, what does that mean? Well, that means that these are elements of the domain. They're elements from V, such that when we have t acting on x, we're going to get a zero vector in the codomain. And the same thing with y, right? T of y is also going to equal the zero vector. Okay. So we know that x and y must satisfy these two properties because they're in the kernel. Now we just want to show that a linear combination, lambda x plus mu y, is also in the kernel. So let's do that. Let's write out that linear combination. So we're going to have lambda x plus mu of y. And we would ideally like to show that when we apply t to this, we get the zero vector. So let's see what happens when this is some vector, right? So we can apply t to it. And let's see what happens when we apply t to this vector. Well, we know that t is a linear map. So if t acts on a linear combination of inputs, we will in turn get a linear combination of outputs. So this is going to equal lambda t of x plus mu t of y. Just again, according to what it means to be a linear map. And then at this point, we just substitute in what these are equal to. We know that t of x maps to 0, and we also know that t of y maps to 0. So this right-hand side right here is going to become lambda times the zero vector plus mu times the zero vector. And this is just equal to the zero vector. Therefore, we've shown that lambda x plus mu y, this is an element of the domain, that when we apply t to it, we eventually get to the zero vector in the codomain. Therefore, lambda x plus mu y is in the kernel of t, meaning that the kernel of t is a subspace of the domain, a vector subspace of the domain V. Okay. So hopefully line by line that makes sense, but I want to make sure big picture that makes sense as well. So some of the fundamental subspaces that we're often interested in, like the image and the kernel, it turns out that they are also vector spaces. They're not just these arbitrary subsets. And they are vector subspaces when they are, when the map that we're looking at is a linear map. Just another reason why we care so much about linear maps. Some of the fundamental subspaces of linear maps are also vector spaces, and that will not always be true for an arbitrary map. Notice that in both parts of this proof, whether we were looking at the image or the kernel, we inherently needed to use this property that the function on a linear combination of inputs is equal to a linear combination of outputs. Okay, so hopefully this makes sense, and why, in at least in motivating why we care so much about linear maps. Now, what I'm going to, I guess that's all we're going to have for this video. I think this is probably a good point to call it here. In the next video, we're going to take a closer look, or a more specific look at linear maps. This was kind of motivating, well, first what they are, but also why they're important and why we should care about them. You might have heard of the term matrices in linear algebra, and matrices are just these notoriously, these concepts that are just notoriously misunderstood because I don't think, at least when I first learned about them, the proper context was not given behind what a matrix was. And part of this video is just to motivate what a matrix is. So in the next video, we're going to probably introduce matrices and to just really see, okay, that's all a matrix is. It doesn't need to be this complicated whatever thing. It's just this. Okay. So I'm looking forward to it. Hopefully you guys are as well. And yeah, thanks so much for watching. I'll see you guys in the next one.